Nazi engineers train explosive dogs to blow up tanks. Railway cannons weighing 1,350 tons fire shells heavy as cars. Bats carry fire bombs into Japanese cities made of paper and wood. But which bizarre weapon proved too dangerous even for its own creators? When war consumes everything, armies need more than just soldiers and plans. They need wild ideas, urgent action, and the nerve to try anything that might work. During World War II, every battlefield became a testing ground. Smart thinking wasn't just helpful anymore. It became life or death. New weapons appeared faster than ever before. The pressure to beat the enemy, fight back, or destroy them first pushed inventors to work at lightning speed. Battles became impossible to predict. Engineers designed bombs that flew on living wings. They built cannons so huge they needed entire trains to move them. They trained dogs to blow up tanks. They created weapons so weird that even their makers wondered if they would work. Nothing seemed too crazy if it might help win the war. Being clever became dangerous. Science turned into another kind of battlefield. What happens when smart thinking gives way to desperate action? What kind of war begins when all the rules disappear? And how many of those wild ideas survived after the fighting ended? This was total war, the birth of uncontrolled invention. World War II changed forever how science and destruction worked together. Between 1939 and 1945, the world saw technology advance faster than ever before. The desperate need to win pushed engineers, scientists, and military designers far beyond normal limits of weapons making. This wasn't just a war of numbers or strategy, it was a ruthless race for the best technology. Each side spent enormous amounts of money searching for that perfect weapon that would tip the balance toward victory. The whole idea of military invention changed completely during these 6 years. Things that used to take decades to develop in peacetime now had to be ready in months or weeks. The constant pressure of active fighting turned battlefields into test labs where barely tried prototypes faced enemy fire directly. This extreme rush created developments that challenged not just military thinking, but the very laws of physics and engineering. Germany led this race toward the extraordinary. The Nazi government built an unmatched military science system. They gathered thousands of engineers in secret places like Peenemünde, where the first guided missiles in history were born. Under Albert Speer's armament ministry, special units emerged like the Special Weapons Office. This group handled ideas too radical for normal departments. This German obsession with extreme technology got stronger as the war turned against them. It fed their propaganda about miracle weapons that would supposedly change the fate of their nation. The Nazi belief in wonder weapons wasn't just propaganda. It was military policy that put disruptive innovation over mass production. While the United States built thousands of B-24 bombers and the Soviet Union produced huge numbers of T-34 tanks, Germany bet on creating a dozen revolutionary prototypes. This approach created real innovations that influenced later decades. But it also produced devices whose usefulness bordered on the absurd. On the other side of the Atlantic, Great Britain responded with its own version of extreme experimentation. Winston Churchill authorized the creation of the Special Operations Executive. This organization combined traditional spying with radical technology innovation. SOE labs developed everything from explosive pencils to sabotage devices disguised as everyday objects. At the same time, the Directorate of Miscellaneous Weapons Development worked on projects that went beyond normal limits. From swimming tanks to rockets powered by giant wheels. The United States established the Office of Strategic Services, which later became the CIA. This group brought scientists from top universities into classified programs. American labs didn't just work on the atomic bomb. They explored everything from mind control chemicals to systems that used animals for combat missions. American industrial power allowed even the wildest ideas to get funding and complete development. Some reached testing phases with unexpectedly destructive results. The Soviet Union, facing the biggest invasion in history, adopted a practical but equally radical approach. Soviet thinking focused on simple and cheap solutions that could be used quickly at the front. This led to systems that looked primitive, but proved really effective in combat. The Red Army experimented with biological resources, basic remote control devices, and tactics that broke all previous military rules. Japan, cut off geographically and limited in resources, developed a military philosophy that combined samurai tradition with extreme technology innovation. Their doctrine of total sacrifice became real in weapons designed specifically for suicide missions, from manned rocket planes to tiny submarines. These weren't desperate last-minute ideas. They were planned, tested, and actually used developments. They reflected a military mindset that put psychological impact and destructive efficiency over keeping the operator alive. This worldwide push toward radical military experimentation produced weapons that challenged normal categories. New devices emerged that combined airplane engineering with animal control systems. Others mixed rocket power with wooden structures. Vehicles redefined basic concepts like movement, armor, and firepower. Many of these creations worked well in specific situations. Others failed spectacularly. All represent real proof of an era where the line between innovation and desperation became impossible to see. Time was the key factor in this evolution. Unlike peacetime periods where new military technology developed slowly over decades, World War II compressed complete cycles of research, development, testing, and use into periods that rarely lasted more than 2 years. This speed-up produced genuine advances that laid foundations for later developments. But it also created an extraordinary number of projects that, although they worked, proved impractical for real war. The Krumlauf was a weapon that tried to solve an impossible problem. How do you shoot around corners without getting shot yourself? The brutal street fighting in Stalingrad had taught a deadly lesson. The first soldier to turn a corner rarely lived to tell about it. This harsh reality forced German engineers to develop a solution that defied the basic laws of how bullets fly. They wanted a gun that could fire at an angle, letting the shooter stay hidden behind cover. The idea came from reports from the Eastern Front. House-to-house fighting showed clear patterns. Most soldiers died when moving through narrow hallways or turning corners in bombed buildings. German army statistics proved that assault units suffered huge losses in these situations. To fight this constant threat, military leaders approved urgent development of a system that would reduce risk in city fighting. The solution had to be easy to carry, cheap to make, and work with existing weapons. The Krumlauf was designed to modify the Sturmgewehr 44 assault rifle. It would allow firing around obstacles without direct exposure to enemy fire. The Krupp company was given the job of making this concept real. They designed versions with curves of 30, 45, 60, and up to 90 degrees. Each was meant for different uses. The steeper angle versions were intended for armored vehicles, especially in blind spots where direct aiming was impossible. The 30-degree version was the only one made in significant numbers. It offered the best balance between strength, firing accuracy, and how long the barrel would last. The Krumlauf wasn't simply a curved tube. The design included a periscope system that let the operator aim without sticking his head out. This sight used a set of mirrors mounted at angles and protected by a metal case. To avoid ballistic problems, special rifling was developed to guide the bullet through its curved path. However, this adaptation put enormous stress on the barrel structure and the bullet itself. Lab tests showed that bullets suffered gradual damage, especially after more than 250 shots per unit. German engineers faced multiple technical challenges. One of the main ones was bullets breaking apart inside the barrel. In many cases, the bullet couldn't handle the forced turn inside the barrel and broke apart. This created a chaotic firing pattern similar to a shotgun. This drastically reduced penetration and affected shooter safety. Despite attempts to strengthen the bullet, the problem continued because of the physical laws involved in such a forced curve. Training troops required relearning how to see and aim. The periscopes flipped spatial orientation and changed depth perception. User manuals included specific exercises to recalibrate aim and understand how the curve affected where bullets went. Selected units practiced with moving targets and objectives protected by artificial corners to simulate real urban combat. The Krumlov showed that even the most unusual ideas could have some practical use. But it also proved that physics has limits that can't be overcome by engineering alone. When American air defenses became impossible to penetrate with normal Japanese aircraft, the Yokosuka Naval Arsenal came up with a response that completely eliminated the idea of coming back home. They designed a manned flying bomb built to overcome any interceptor through pure speed. This was the MXY-7 Oka, whose very creation represented a radical change in weapons thinking of its time. The logic behind the Oka was direct and brutally practical. American fighters were systematically shooting down Japanese bombers before they could get close enough to their targets. Normal bombs failed against the reinforced armor of battleships and aircraft carriers. In this situation, the only way to guarantee a direct hit was to combine the weapon and the pilot into a single system. The Oka design completely eliminated any unnecessary element. No landing gear, no instruments for return trips, no backup navigation systems. Everything served a single purpose: to carry a massive explosive charge at maximum speed against a naval target. The body was built with a combination of aluminum and laminated wood. This responded to the double need for lightness and material availability. This configuration reduced weight without completely compromising structural strength. A central explosive charge of 1,200 kilograms of high explosives was housed in the front part of the body, designed to detonate after penetrating the target. At that terminal speed, even battleships with reinforced armor were vulnerable to direct hits. Power came from 3 Type 4 solid fuel rockets developed by Kayaba Kogyo. Each burned for 10 seconds. Together, they provided 800 kilograms of thrust, enough to take the Oka from an initial gliding speed to more than 580 miles per hour in its final phase. This brutal acceleration made it almost impossible to intercept by American escort fighters in the critical seconds before impact. However, the design had a severe structural limitation. The Oka needed to be carried to the launch point by a Mitsubishi G4M2 Betty bomber. This aircraft had to get within less than 20 miles of the naval target before releasing the weapon. For that phase, the Oka descended gliding to an optimal operational altitude. At that moment, the rockets were fired. This complete dependence on the mother bomber became the fundamental weakness of the system. Japanese bombers, large and slow, were priority targets for American fighters. Many were shot down before even reaching the release point. This situation compromised the complete system. The loss of a single bomber meant the destruction of the Oka and its pilot before even beginning the mission. Despite air escorts of Mitsubishi Zero fighters, Allied air superiority in the Western Pacific made it extremely difficult to successfully complete the deployment cycle. Training Oka pilots was specific and fast. Many of them were young men without real combat experience. Their preparation centered on gliding control, spatial orientation at high speed, and identifying naval targets from medium altitudes. Motorless gliders were used for initial instruction. The Oka controls were deliberately simplified, reduced to the minimum necessary to adjust elevation and direction in the last seconds. No escape mechanism existed. Once the descent began, the pilot became part of the weapon. Operational deployment began in the Battle of Okinawa in April 1945. The formations consisted of waves of bombers, each carrying an Oka underneath. In total, Japan produced more than 850 units. Although only 74 were launched in real combat, most were destroyed before reaching activation distance. In some cases, the enemy managed to detect the approach and maneuver out of the attack angle before impact. Nevertheless, successful impacts showed considerable destructive power. The USS Manert El Abel, an American destroyer, was sunk after a direct Oka impact. marking the first confirmed victim of the system. Other ships, although not sunk, suffered severe structural damage. The explosive penetrated the deck and produced massive fires in internal compartments. Technical naval reports from the U.S. Navy noted that the Oka's impact speed exceeded normal reaction times of short-range anti-aircraft systems, making it especially difficult to stop in its terminal phase. Despite its limitations, improved versions were developed, such as Model 22, which replaced the rockets with a Su-11 jet engine, significantly expanding operational range. This redesign required modifications in the body structure, increasing fuel capacity and reinforcing key sections. However, it wasn't implemented widely before Japanese surrender. The Schwerer Gustav was not simply a large cannon. It was the extreme symbol of a military logic that took the concepts of firepower, advanced metallurgy, and operational logistics to their limit. With a total weight of 1,350 tons, shells heavier than a family car, and a length of almost 154 feet, this railway gun represented the peak of heavy artillery in modern warfare history. In 1934, the German High Command asked the Krupp Company for a design that on paper seemed impossible to build. They wanted a weapon capable of destroying reinforced concrete fortifications 23 feet thick or penetrating steel armor 3 feet thick while staying out of reach of enemy artillery. This request was based on studies of French defenses of the Maginot Line. Although the weapon wasn't completed in time to be used against them, the result was the Gustav, whose design required completely re-engineering the concept of mobile artillery. The cannon had a tube 107 feet long with a caliber of 31 inches. Its structure required a double parallel railway track to distribute its enormous mass. 80 special wheels mounted on 5-axle bogies supported the load on 2 articulated chassis. This complexity was necessary to handle recoil, maintain balance during firing, and provide stability on variable terrain. The Gustav's ammunition was as extraordinary as its size. 2 main types of shells were designed. One explosive shell weighing 10,580 pounds with a maximum range of 29 miles, and another armor-piercing shell weighing 15,650 pounds that could hit targets at 24 miles with force capable of penetrating underground bunkers. Each shell required loading with a special crane and was accompanied by separate propelling charges inserted manually by trained operators. The loading operation alone could take up to 45 minutes. Building the Gustav was an unprecedented metallurgical challenge. Krupp developed special steels with progressive heat treatments to withstand the internal pressures of firing. Forging the main tube took several months, and its assembly required customized industrial installations. The cannon was tested for the first time at Rügenwalde, where controlled shots were conducted to verify structural integrity, precision, and recoil behavior. These trials revealed that the cannon needed constant adjustments in its railway suspension system due to tiny deformations caused by the shots. Operating the Gustav demanded an unprecedented mobilization. Between 4,000 and 5,000 soldiers were required, plus more than 20 special wagons, hauling locomotives, assembly cranes, and qualified technical personnel. Building the parallel track took from 3 to 6 weeks depending on terrain. In addition, defensive positions, camouflage, command centers, and heavy anti-aircraft batteries had to be established to protect the position against Allied attacks. The only operational use of the Gustav occurred during the siege of Sevastopol on the Crimean Peninsula in June 1942. The weapon was transported by train through Poland and Ukraine to the railway port of Bakhchisaray, where it was mounted on a special track built for the purpose. From there, between June 5th and 17th, the Gustav fired 48 shells, destroying multiple heavily fortified targets, including underground ammunition storage and Fort Stalin Fortress, which had resisted conventional attacks. Craters up to 100 feet in diameter and structural damage of great depth were recorded, confirming that the weapon was technically capable of fulfilling its original function. However, practical problems became obvious. The rate of fire was extremely slow. A single shot every 30 to 45 minutes due to reloading time, alignment, and pressure checks. The cannon required barrel replacement every 50 shots due to internal wear. Added to this was the system's vulnerability to Allied aviation. Any successful air attack could render the entire operation useless in minutes, despite mounted defenses. A second unit was built called Dora, which was deployed near Stalingrad but withdrawn before being used. There are no confirmed records of operational shots from Dora. The Gustav was technically perfect, precise, powerful, and structurally solid. But its design responded to a type of static and planned warfare that no longer existed in 1942. Modern warfare demanded mobility, adaptability, and rapid deployment. The Gustav couldn't move with agility, couldn't fire while moving, and needed weeks of logistical preparation. It was a solution from the past used in a future conflict. While German panzers advanced without effective opposition across the vast Soviet steppes in 1941, the Red Army faced a critical limitation: the lack of anti-tank weapons capable of stopping modern armored vehicles like the Panzer IV, the Tiger I, or the WW2. This structural shortage led to non-conventional solutions. Among them, one of the most radical was the use of explosive dogs as living anti-armor units. The project wasn't improvised. It was the result of systematic research begun several years before the conflict. In 1935, the Military Canine Service began experimenting with using dogs in offensive military applications. Soviet military thinking anticipated mechanized conflicts with technologically superior enemies, especially in scenarios where Soviet forces could find themselves outnumbered or outgunned. The central method was based on training through rewards. Dogs were trained, mainly German shepherds and large mixed breeds, to associate armored vehicles with food. For weeks, the animals were fed exclusively under stationary Soviet tanks. Then engine noise and slow movement were introduced. The progression reached real vehicles in motion. In theory, this created an automatic response. Upon hearing or seeing a tank, the dog instinctively headed under it looking for food. The standard explosive charge consisted of 22 to 26 pounds of TNT installed in a reinforced canvas harness. This harness was designed to distribute weight in a balanced way and allow complete mobility. A vertical lever stuck up over the animal's back, activating the detonator by contact when the dog went under the vehicle's chassis. The system didn't use timers or remote control in its original version. The explosion happened by direct physical contact. Each combat unit with bomb dogs operated as a specialized platoon of 27 dogs divided into squads of 9, each with their handlers. These soldiers received specific training in dog handling, tactical deployment signals, and evacuation procedures in case of error. Transport to the front was carried out in GAZ AA trucks adapted with ventilated compartments. The animals were unloaded at short distance from German lines and released upon receiving visual or sound signals. The first significant deployment took place in autumn 1941 during defensive operations before the Battle of Stalingrad. Operational reports from the 62nd Army show the destruction of 3 German vehicles during a coordinated attack. However, critical problems immediately arose. Many dogs trained with Soviet tanks didn't adequately tell the difference between enemy and friendly armored vehicles. More than once, the animals returned toward Soviet trenches, setting off the charge in Allied positions and causing significant casualties. In the Caucasus campaign, a unit from the Transcaucasian Front suffered total failure. Under intense artillery fire, the dogs became confused, ran in multiple directions, and caused uncontrolled explosions. Casualties included both Soviet personnel and their own animals. These events confirmed one of the structural limitations of the system: the impossibility of controlling animal behavior under real combat conditions. The German High Command didn't take long to react. Specific countermeasures were put in place. Immediate shooting of any dog seen in combat zones was ordered. Dog hunting patrols were established and tactical bulletins were issued warning about the possible use of animals as mobile mines. However, distinguishing between civilian and trained animals was difficult in rural areas of the Eastern Front. reducing the effectiveness of these measures. Despite initial failures, the program continued. Technical modifications were introduced to improve reliability. An updated version of the harness included automatic charge release if the dog didn't reach a target in estimated time. Another variant included remote detonation via cable or radio frequency. Although this technology was limited by interference and device fragility in real combat, to improve target identification, dogs were trained using captured German vehicles, thus avoiding confusion with Soviet units. The largest documented deployment of bomb dogs occurred during the Battle of Kursk in 1943. More than 300 dogs were used in massive attacks against German armored units of Army Group Center. Results were mixed. While 16 tanks were damaged or destroyed according to Soviet figures, many animals died before reaching their targets or detonated out of range. Even so, the presence of explosive dogs on the field created a psychological deterrent effect among some German units. From a technical point of view, bomb dogs represented a high-risk weapon with variable performance. Their success depended on unpredictable factors such as weather, visibility, animal mental state, and evolving tactical situation. Unlike static mines or portable anti-tank weapons, the dog was an unreliable semi-independent platform, but its production cost was low, required little advanced technology, and its training could be completed in a few weeks, making it viable for an army with limited resources. The letter that changed the course of biological warfare arrived to Franklin Roosevelt from an unexpected place, Dr. Lytle S. Adams' dental office in Pennsylvania. After observing bats in Carlsbad caves, Adams proposed an idea so wild that the president considered it crazy enough to work. The plan was to convert flying mammals into carriers of firebombs against Japanese cities made of wood and paper. Roosevelt referred the proposal to the War Department, starting Project X-ray under supervision of Dr. Louis Fieser from Harvard's chemistry laboratory. Fieser's previous experience with napalm made him the ideal candidate to solve the technical challenges of making fire weapons small enough to be carried by bats. Species selection centered on Mexican free-tailed bats, abundant in the American Southwest. These animals had ideal characteristics: significant load capacity relative to their size, predictable shelter behavior in structures, and resistance to altitude and pressure changes during air transport. Individual firebombs weighed just over half an ounce, containing concentrated napalm sufficient to start fires in burnable materials. Chemical timers provided delays of 20 to 30 minutes, allowing bats to find shelter in structures before ignition. Attachment systems used tiny clips and surgical collars that didn't interfere with natural mobility. Specialized cylindrical containers kept up to 1,040 bats in forced hibernation through controlled refrigeration. This approach took advantage of natural body responses to reduce temperatures, keeping them inactive during bombing flights. Parachute systems controlled descent speed for gradual spread in patterns that maximize target area coverage. Tests at Muroc, California, included behavioral evaluation after artificial hibernation, analysis of aerial spread patterns, and timer verification under variable conditions. Experiments confirmed that bats followed natural shelter instincts, seeking dark spaces typical of attics and basements where fires could spread rapidly. In May 1943, an accidental escape at Carlsbad Army Airfield accidentally proved destructive effectiveness. Several bats equipped with fire devices took shelter in base hangars, starting uncontrolled fires that destroyed maintenance installations. This incident, documented as unintentional verification, reinforced confidence in the technical viability of the concept. Later controlled tests used mock-ups of Japanese cities that reproduced traditional construction methods. Results confirmed that a B-24 bomber loaded with containers could start more than 3,500 simultaneous fires spread across an extensive urban area, surpassing any conventional fire attack. However, maintaining massive bat populations required specialized installations, trained personnel, and feeding systems that demanded significant resources. Coordination with bombing operations presented complications related to timing, navigation, and release procedures that required extensive aircraft modifications. The time factor proved critical. While Project X-ray progressed, the Manhattan Project advanced toward nuclear production that promised destructive capabilities superior to any conventional system. In August 1944, General Leslie Groves requested absolute priority for resources, resulting in official cancellation of the BAT program. The decision reflected strategic calculations that prioritized nuclear concentration over experimental approaches. Analysts concluded that although technically viable, the system would require development periods that exceeded operational schedules to end the Pacific War. Few weapons in military history have combined extreme technical ambition with such spectacularly catastrophic results as the Great Panjandrum. This rocket-propelled explosive wheel represented the peak of British experimentation during preparation for Normandy. It was a device that promised to revolutionize beach warfare but ended up being more dangerous for its operators than for the enemy. The Directorate of Miscellaneous Weapons Development conceived the Panjandrum as a radical solution for the coastal defenses of the Atlantic Wall. Planners recognized that German concrete walls and anti-tank obstacles would require massive explosive charges placed with precision. This was a task that exceeded the capabilities of naval artillery or conventional aerial bombardment. The configuration consisted of two giant plywood wheels, 10 feet in diameter, connected by a central axle that housed 4,000 pounds of high-power explosives. Cordite rockets installed radially around the rim would provide directional push, theoretically propelling the device across the beach toward target fortifications. The operational concept assumed launch from vessels in shallow waters, followed by self-propelled movement through synchronized rocket activation. Without remote control systems or active steering, trajectory depended completely on precise timing and uniform wheel resistance on variable surfaces. This dependence on ideal conditions immediately became the fundamental weakness of the system. Tests began in September 1943 at Westward Ho, Devon, a beach selected for topographical similarity to Normandy. But its non-classified nature allowed unauthorized observation by civilians and even filming by Path News. The first trial revealed catastrophic problems. Uneven rocket ignition caused uncontrolled spinning, severe sideways tilt, and total loss of direction. The Panjandrum spun violently, moved off the planned course, and stopped when multiple rockets detached due to excessive spinning forces. Correction attempts included a third central stabilizing wheel and guide cables connected to coastal controls. These modifications introduced additional complications without resolving fundamental problems. The third wheel interfered with ability to cross obstacles while cables tangled with rotating rockets and broke during the first phases of movement. Rocket detachment during operation created extreme dangers for observers and technical personnel. Released rockets flew unpredictably with unburned fuel, hitting observation positions and forcing temporary stops while safety rules were revised. The most documented demonstration occurred before senior officers and Ministry of Supply representatives, designed to show viability before approval for production. The Panjandrum traveled barely 130 feet before experiencing catastrophic failure. Multiple rockets detached simultaneously, causing total loss of power and partial detonation of explosives due to damage to safety systems. Official observers concluded that the device presented unacceptable risks for Allied forces. These included premature detonation, unpredictable trajectory toward own troops, and dangerous fragmentation in areas densely occupied by military personnel. Final evaluation determined that no feasible modification could resolve fundamental limitations of stability and control. The program was officially canceled in 1944, freeing resources for projects with greater probability of effectively contributing to Normandy operations. No Panjandrum was deployed during D-Day. Prototypes were taken apart with recoverable materials, redirected toward conventional systems. The Great Panjandrum conundrum perfectly shows how technical ambition without adequate consideration of fundamental physical principles can produce systems that, although conceptually innovative, fail spectacularly in practical application. In the basement of the Kubinka Tank Museum rests one of the deepest mysteries of World War II, an armored vehicle of spherical configuration whose purpose, specific origin, and operational circumstances defy decades of specialized research. The only known Kugelpanzer represents the most extreme example of German experimentation in vehicle design. It's an artifact that seems more appropriate for science fiction than for historical battlefields. Soviet troops discovered this enigma during the occupation of Manchuria in August 1945. Although exact circumstances remain undocumented, circumstantial evidence suggests discovery in Japanese installations, possibly as a result of Axis technology transfers. These included advanced torpedoes, rocket engines, and other German developments transported by Type 9D submarines. Dimensions confirm design for individual operation: 5 feet in length, 4 feet in height, 3 feet in width. Structural configuration is based on 2 completely enclosed metal wheels forming the sides, connected by a central cylindrical compartment that contains the operator's cabin. A rear stabilizing roller prevents overturning during irregular movement. Armor protection is deliberately light, between 5 and 8 millimeters thick, sufficient only against fragments or small arms fire at moderate distances. This limitation clearly indicates that the vehicle avoided direct combat, suggesting roles that emphasize stealth, reconnaissance, or specialized support rather than frontline fighting capability. Access requires adopting an almost fetal position within the extremely confined space, severely limiting operational duration due to physical fatigue and claustrophobia. This configuration indicates intended use for brief missions or specialized applications that justified extreme habitability limitations. Vision is provided through a front slot protected by sliding cover, but without advanced optical systems, telescopic sights, or aiming equipment typical of military vehicles. This absence suggests dependence on direct observation, limiting effectiveness in reduced visibility conditions. No identifiable mounting points for weapons exist, although speculation suggests possible space for light machine gun aligned with the vision slot. However, absence of physical evidence of weapons systems, ammunition, or control mechanisms reinforces conclusions that it wasn't designed for direct combat. The original propulsion system was removed or never completed during capture, complicating analysis of mobility capabilities. Technical evaluations suggest that a small motorcycle engine would have provided adequate power with differential transmission controlling lateral wheels for directional maneuvers. Absence of conventional suspension indicates dependence on large wheels for impact absorption. Manufacturing marks confirm German origin associated with Krupp, but no records exist in declassified archives documenting specifications, production numbers, or operational assignments. This absence suggests extreme classification or development under special authority that avoided normal administrative channels. The most believable theory proposes use as reconnaissance vehicle for stealthy infiltration, taking advantage of its unusual visual profile that would confuse identification at distance. The spherical shape would provide effective camouflage when still, especially in terrain with dense vegetation where it could be confused with natural formations. Alternative theories suggest use as liaison vehicle for communications between isolated positions, taking advantage of compact size for mobility in tunnels, trenches, or urban areas where conventional vehicles couldn't operate. A third hypothesis proposes specialized defensive function for critical installations like airfields or depots, where perimeter patrol would provide continuous surveillance without dedicated personnel. Compact design would allow operation in confined spaces typical of underground installations or bunkers. Presence in Manchuria confirms transfer from Germany as part of technology exchanges that included multiple prototypes transported by German submarines. The fact that only one example has been discovered suggests it never progressed beyond experimental phase or that production was extremely limited. The Kugelpanzer remains as real proof of radical German experimentation, when operational pressure and wonder weapon ideology drove exploration of concepts that challenged established principles of vehicle design. Its preservation in Kubinka ensures that future generations can study physical evidence of one of the most unusual experiments in armored vehicle development. It provides perspectives on the limits of technical innovation under total war and the willingness of military organizations to explore radical solutions when conventional methods seem inadequate for specific operational challenges. These weapons and vehicles represent more than failed experiments or successful innovations. They show us what happens when human creativity meets the desperate pressures of total war. They remind us that in the darkest moments of history, the line between genius and madness becomes very thin indeed. The legacy of these unusual weapons lives on in modern military technology. The principles behind guided missiles, precision munitions, and unmanned systems all trace their roots back to the wild experimentation of World War II. Sometimes the craziest ideas turn out to be the most important ones of all.